Okay, good morning, guys. Can you hear and can you see the screen?
Yes, sir.
All right, let's begin. So today it's angular motion, right? And you guys would have done some problems with Mr. So, and I'm just gonna review them for you and answer any other questions that you might have. Okay. So first, we just gotta briefly go over the formulas, right? The first one, this distance here, S, is equal to R, which is a radius, times theta, which is an angle in radians, right? Essentially, what that's saying is that, let's say we have a circle, right? Pretty bad, ugly circle, but okay. Some radius R. I wanted to know the length of some sector, right? And that sector has some angle theta. As long as that theta is in radians, it works out really nicely so that we can just multiply it by the radius R and we get the length here of this part, right? S. And that's kind of one of the main motivations for using radians, because little things like those work out really well as opposed to using degrees. And then there are your other formulas, which are essentially just angular versions of the old ones we have. Like this one is similar to V is equal to U plus AT. But here, this A becomes alpha, a new symbol, which refers to angular acceleration, right? Acceleration. T, of course, is time, as usual, and W0, WO, right? Angular velocity, initial angular velocity, final angular velocity, right?
WO is initial.
Yeah, so this is essentially just initial, final, and this here is angular acceleration. So it's just the same formulas from before. It's just we change the symbols and we use the angular version, right? Angular velocity, angular acceleration, angular velocity, right? Okay. Similarly here, we know this comes from S is equal to UT plus half AT, right? Angular acceleration, half AT squared, time again, half. So this part makes sense, right? Initial velocity, W0 times T again, same thing, right? Now, theta here refers to angle and not distance. But we know the distance comes from this, right? So there's a difference between essentially what we call like this angular movement, right? This angular coverage, which we represent by theta, and the linear distance that corresponds to, right? So you can think of this as saying that because angular velocity, right, would be in something like rads per second, right? And regular velocity would be something like kilometers per hour, right? So in regular velocity, we're covering kilometers with some particular time. In angular velocity, we're covering radians in some particular time. So what we're covering essentially is angle, right? The angle is covered. Or revs per second, which is the number of revolutions we go around, which is essentially just saying angles covered. So we're not really looking at what distance is being moved, like linear distance is being moved, but how much angle of coverage we get. So that's why here, instead of S, we use theta. Okay, and now the other one, we remember that big formula, right? V squared is equal to U squared plus 2AS, we just learned that theta is now the new S, right? Angular acceleration, change from acceleration, right? Initial velocity squared, final velocity squared, final velocity squared. So these formulas shouldn't be too unfamiliar to you. You just swap them out with the angular versions, right? Now, two new formulas. Torque is equal to inertia times acceleration. Now, there's a lot of theory behind this. And of course, you can just read that from your handout. And remember from last semester that inertia is equal to mass times k, where k is the radius of gyration, right? Okay. So because you guys did moments and stuff, torque is essentially just force by some distance. So these should all work out and make sense to you. And I write in the handout, so you can go over them on your own time. All right, good. So let's just start working number 7. Now, number 7 is pretty easy, right? A grinding wheel has a radius of 100 millimeters. What is the linear velocity of a point on the rim of a wheel when it's rotating 50 reps? 50 reps. So first and foremost, what's angular velocity? Angular velocity is this right here, right? Revs per second. So how do we convert revs per second? Revs per second, revs referring to the number of revolutions. Revolutions per every second. So there's something spinning. In this case, it's a grinding wheel. And it goes around 50 times. Let's say there's just some point on it. This point would go around 50 times every second, right? Now, how do we change that to the linear version? Well, we know S is equal to R times theta, right? So if you want to change this to velocity, linear velocity, so this S here, we know linear velocity is some S divided by some time, right? So here would be R divided by some theta divided by some time. And this here, this term here is actually just omega, right? And this term here is actually just velocity. So V is equal to RW. And this is another equation you should make note of, but it's fairly intuitive. For when converting from linear velocity, from angular velocity to linear velocity, you just multiply by the radius. When you convert from this angular distance here, this angular measurement of distance to linear distance, we just multiply by R. And it's also the same with acceleration. So we want regular acceleration. If we're converting from angular acceleration to regular acceleration, we just multiply by R. Okay? So using that formula, we plug the values in. R, the radius of the grinding wheel, is 100 millimeters, right? Of course, we want meters per second, which is our general units that we usually use. So 100 divided by 1,000 give you 0.1 meters. Now, remember, for the S is equal to R theta here, this theta needs to be in rads, right? Rads. Or for V is equal to R, W, is W needs to be in rads per second. So we need to convert this 50 revolutions to rads per second. So the amount of radians in an entire circle is equal to 2 pi, right? So usually in degrees, you'd say a circle has 360 degrees. For radians, a circle has 2 pi radians, right? So when we say we go around 1 revolution, we're covering 2 pi, 2 pi, 2 pi. So if we go around 50 times per second, what we're actually covering is 2 pi times 50 radians per second, right? And you can generalize that, saying that n revs per second is equal to 2 pi n radians per second. Okay. Now with all the foundation laid, we can just multiply that out and say V is equal to 10 pi, 2 by 50, 100 times 0.1, which since dividing by 10 is 10 pi meters per second. And 10 pi meters per second is 31.416 meters per second. Any questions on this?
So you convert the 100 to meters first.
Yeah. And you convert the revs to rads. Okay, because 50 revs per second is equal to 2 pi 50 rads per second. Right? So n revs per second is equal to 2 pi n rads per second. Just multiply that out and you should get this answer. You can do this intermediate step if you like. Okay.
Sir, before you move on, sorry. Sir, when I put 0.1
Could you wait a
times
second?
2 pi 50.
There's a plane flying
Alright.
over. Yeah, okay, go ahead.
Yes,
go
sir.
ahead.
Yes, sir. When I plug in 0.1, 2 pi 50 in my calculator, sorry, telling me error.
So did you do 0.1 times 2 times pi times 50? Or did you just do 2
Oh, no,
pi?
sir. I put it in the bracket like over on the screen.
Okay. Try putting 2 times pi. Depending on the calculator, you might need to specify the multiplication, right? Maybe you can kind of do this in your head, right?
Oh, yes, sir. I get it now. Yeah, I got it.
This here is
Yeah.
2 pi 50. This here is 100 pi. 100 pi times 0.1. This is kind of like dividing by 10. So then you know that's 10 pi. Right? We know pi is 3.1416. Multiply that by 10, 10 pi, you get right, third of 1.416. Easy, right?
Yes, sir.
Good. All right, so moving on to number 9. Number 9 is a little bit more work. Slightly more, not too much more. Okay, so the armature of an electric motor is running at 50 revs per second. When the current is switched off, the armature comes to rest in 12 seconds. What is A, the average angular retardation? And B, the number of revolutions made by the armature in coming to rest? Okay, so the number of revolutions made is obviously referring to some distance theta, right? But they want it in revs instead of rads. And we know average angular retardation is that fancy symbol, right? At alpha. Now, what they gave us here is some velocity, right? 100 revs per second. So we can use that to find angular acceleration or angular retardation using this 12-second time we have, right? So our formula for that. And now remember, you need to start thinking of these things the same way you thought about regular velocity and regular acceleration, right? It's just that they're angular now. So if we had some velocity, we needed to find some acceleration and we had a time, right away we would know V is equal to U plus AT, plug our values in, manipulate, and solve for A. Same way, right, when we see these values, we should know already omega 1 is equal to omega 0 plus alpha t, plug our values in, manipulate, right? So the armature of the electric motor starts off at 100 revs per second, right? Initial velocity, 100 revs. Then it comes to rest in 12 seconds, right? Comes to rest, so 0. So here we solve this, 0 minus 100 divided by 12, right? You can manipulate the formula first, plug the values in, and we get the answers. Now remember, this is revs, 100 revs. So now the answer, we need to realize that that's going to be in revs per second squared. So that there, when you divide this up, is going to be 8 1/3 revs per second squared, right? And it's minus, right? Because retardation, right? But if you call it retardation, you don't need to put the minus sign. If you call it acceleration, then you put the minus sign, right? Now, converting that to rads, right? We just multiply by 2 pi, right? So 8 by 2, 16, 1/3 by 2, 2/3 pi rads per second squared. Working this out, just plug it into the calculator, 16 2/3 pi, you get 52.36 rads per second squared. Okay. Now, alternatively, from the start, you can go ahead, like from right here, instead of putting in 100 here, you can do 2 pi 100, right, which is 200 pi, and go about your work from there. And you should get the same answer.
Wait, sir, you just said that if it's retardation, you don't have to put the minus sign, right? But
Yeah, if you call it retardation, like if you're saying finding like this here, you say like in your final answer, like here, if you
yeah,
just
I
say
understand that, right?
retardation
But
is that, and you don't put the minus
yeah,
sign.
but it has a okay. So just don't put it.
If you say it's retardation, yeah.
Okay then.
Okay. Okay, does that make sense? Because retardation implies that it's a negative
Yeah,
acceleration,
I
right?
understand that it implies that it's slowing down, but it was just that in the formula there's a negative. It's
Yeah.
gonna be negative.
Yeah, there's a negative sign here. I didn't put it in. Okay, great. Now, the number of revolutions made by the armature coming to rest. Okay. So now, number of revolutions, that's some theta, which is equivalent to our S, right? We know the formula for that. Usually would be S is equal to UT plus half AT. So we know that's theta is equal to omega 0 T plus half angular acceleration by time. We gotta plug values in for this. Now, because they want it in the number of revolutions, there's no need to convert, right? To convert. So you just plug in 100 revs here, 100 revs here, omega 0, 100 revs. 12 seconds, 12 seconds, right? Now for the acceleration, here you see the minus sign because this here requires acceleration, right? So -8, 1 divided by 3, right? So now you see the benefit of solving it this way first. Instead of just plugging in 200 pi, right? See the benefit of that. So having that right there, you can just plug those values in. Right? Plug all this into the calculator or do part, and you should get 600 revs. 600 revs. Now, alternatively, some people might just have this part here in radians per second squared, and this part here would be needed to be converted into radians per second. So your answer is going to be in radians. Then you're going to divide that by 2 pi, and you should get about 600 revs. Some people might get 599.5. Okay, good. So any questions on this?
Excuse me, sir. A question.
Yeah.
The velocity, you changing it to rads per second?
No, because
100?
so the number of revolutions made by the armature and come to rest. So they want revolutions. So what I did, so our angular acceleration is this, right? But in between that, I found this. I found it in revs per second. So since I have this in revs per second, and I know 100 revs per second, I can just use both of them as revs per second and get my answer out in revs, right? Instead of doing this, converting it to, instead of putting this in here and putting 200 pi here, I can just use revs and get my answer in revs, which is nice. And it's fairly accurate because we didn't drop any decimal points along the way. Does that make sense? Okay. So I'm sure there are alternative ways to work it, and I'm sure Mr. Sil did a different way. But remember, as long as you're not breaking any rules of math, right? We didn't divide this by 2 pi, so we didn't divide this by 2 pi. All the units work out, right? All the units work out. So therefore you get this units, right? You can do it the other way. Use the same formula and you will get the same answer. But if it works this way as well, if this is in revs and this is in revs, which is very important, you need to make sure that this is in revs per second, right? And not put 52.36 here, you put this value in, right? It'll work out. So. Okay. So any other questions?
Sir, one question for me, right? You see like where you have the fractions, right? The fraction. You necessarily have to put in fractions.
No. Just use calculator.
Okay, so if now I have all right, is the negative 100 divided by 12, and I get negative 8.33. You just put in negative 8.33. I have to put it in the fractions.
No. Just put 8.33. Just put 8.333.
Rest per
fine.
second squared. Okay. All right.
Yeah.
Yes, we're just making sure.
Yeah. Okay. Good. I just like putting it like this because then you just type it in your calculator at the end, and these parts you just work by hand. Okay. Good. Yeah, so no more questions on number 9. Number 10. All right, so you guys know the drill. I'm gonna read this question. You guys can try it out using the angular formula, right? So this formula is equivalent to v squared is equal to u squared plus 2as, right? So we have all of the different things, right? So you guys are gonna work number 10. It's gonna take about maybe 5 minutes, I guess. A wheel initially has an angular velocity of 30 rads. When the brakes are applied, the wheel comes to rest in 40 complete revolutions. What is A, the average retardation, and B, the time taken for the wheel to come to rest, right? Time taken. Yeah, so take a few minutes and work this question. And if you have any trouble, let me know. Yeah, so you guys finished?
Yes, sir.
Anyone else?
Go ahead.
Okay. All right. So yeah, just like the other, it's pretty simple, right? So you plug the values in. We know when the brakes are applied, it comes to a rest. So this obviously here would be 0. Here would be 30 squared. 30 squared, that's about 900. Right, this is 2 alpha times theta, right? Now, this here is in rads per second. So we should obviously want to make these revolutions here in rads, right? So 40 times 2 pi. 2 pi 40 times 2, right? Times alpha. So this is kind of like 2 by 2, 4. 4 fourths, so like 1/60 pi alpha is equal to 900 plus and 0 here. So 900 divided by 1/60 pi should give you this, right? Should give you this. And for the second part, use the other formula, omega 1, omega 0 plus alpha t, right? And then you solve for that with your newfound value for alpha. Nothing too complicated. All right. So number 11, pretty easy. It just uses the torque formula. And again, you should notice how it's Newton meters, right? So you remember from moments from last semester, sometimes we would call it a torque or a bending moment, right? So that intuition should come back into play when you think about, well, what is torque, right? So what torque is required to produce an angular acceleration of 0.4 rats per second squared in a wheel having a moment of inertia of 400 kilograms meters squared? Okay, it's pretty simple. You just plug the values in. I, 400, alpha, rats per second squared, right? You remember you want to keep the values in more or less standard units so that they work out really well, right? So kg is a standard unit for weight, meter standard unit for length, rads standard for that, s is standard for time. Okay. And it should work out. Now, newtons, of course, we know is kg, meters per second squared. And then there's this extra meter here that kind of works out to make this here. This is 1 Newton. And then there's this extra meter here that makes it Newton meters. Now, where does the rad go? Well, we remember that thing, S is equal to R by theta. So it's essentially the same thing where some let's say theta is measured in M. This here is measured in rads. The units kind of just go back to M, right? Because what we're doing is converting this angular representation of distance traveled, and this angular movement to linear distance. So that's kind of why the rad disappears for all of those units. And that's it. That's all there is to it, right? Multiply. Make sure everything is more or less standard, and you get the Newton meters. So try that for number 12. Remember the formula is T, torque, is equal to I by angular acceleration, and where I is inertia, right? Yeah. So the rotor of electric motor has a moment of inertia of 6.0 kg meters squared. What torque is needed to accelerate the rotor at 0.2 rads per second? So take 2 minutes, 3 minutes, and do that. Number 12.
30 seconds, sorry.
Excuse me, sir. Sir? Hello?
Yeah, sorry, we finished.
Yeah, was someone saying something? Was someone saying something?
Yes, sir. Number 10, right, sir?
10. Yeah.
Yes, sir. Number 10 is giving me a little, if you could just, no, number 10, I mean number 10. It's giving me a
10.
little,
Yeah,
it's giving
okay.
me a
No
little
worries.
problem.
We good.
Right, right, sir. I punched in everything in the formula. I probably I ain't do it properly. Right, sir. No, I wonder what I'm going wrong here. So we have
Okay.
the initial is 0.
No, the final is 0. So this one here is 0.
Yes, the
Mhm.
final is
Yeah.
0. Okay.
Good, good. Good.
Right, and the initial is 4, and the initial is 40.
30 squared, right?
Let me see, is 30 squared or
Yeah, in the formula, right?
okay. It's 40 squared.
30 squared, right? Velocity. This
Oh,
here is complete revolutions. 40 is this theta, which you need to multiply by 2 pi.
all right, sir.
So 2 pi times 40, that's like 80 pi, right? And then there's another 2 here, right? So you should end up with something like 30 squared, which is 900 plus 160 pi times alpha. And when you solve for alpha, you get alpha is equal to something like 900 over 160 pi, right? Yeah, and that should give you this answer. Now, when you don't get that answer, then you do use omega 1 is equal to omega 0 plus alpha t. You plug this alpha in that you just get, right? And you solve for time. Remember, this here is 0. This here is 30. You're not squaring it this time, right? So you just use these to solve, right?
Okay.
Yeah. Good. So you just get
So-
30 divided by, yeah. So here you can just get, this here should break down to 30 divided by 1.79, which should give you that 16.76 or something like that, right?
Okay, so yes.
Excuse me, sir. When you get your answer there, it is supposed to be minus, but it's time you find it, so you can just leave it out.
Answer minus.
You carry across the 30, it's supposed to be minus, and then you divide it by the 1.79.
Oh yeah, but retardation
This
is
time-
minus. This is minus
Okay.
here too, right? So it'd be like minus 30 divided by minus 1.79, right? So
Okay,
this
so you
is
cancel out.
yeah. Minus divided by minus is a positive. So it's not minus time. We ain't
Yeah, that's
traveling
what
back.
it is.
Yeah, we're not traveling back to the past or anything like that. There you go. So this question makes sense, right? Right? The guy that was asking you, you got your answer now, right?
So basically, whenever using
Yes, sir.
radians, you use rods. Using rods alone, and when you use revolution, use revolution.
Yeah, what you need to do is make sure, right? Make sure that if you put in your velocities rads, then here needs to be rads as well. This is rads per second. So here, right, could be two possible values. It could be revs or it could be rads, right? If you have here as rads, then here needs to be rads, right? If let's say another question like we were back up here, right? We put this 100 revs here, and then we put revs here, right? Revs here, and then we took revs from the question, right? So if you put revs here, you gotta put revs there. If you put rads here, you gotta put rads there. Whatever formula is, wherever you put rads, you got the other one gotta be rads. Wherever you put revs, the other one gotta be revs, right? You gotta make sure units match. Okay. You got to make sure units match. Right? So like whenever you work a question out, you put in your values, right? You make sure that the velocity you're referring to velocity is velocity, right? Don't accidentally put 40 here, right? Because that's wrong. a 0. Make sure velocity is velocity, plug that in, right? Make sure here is actually angle, so that there. And then when you're done, okay, this is rads, this is revs. Now I gotta change this to rads so that the formula works, right? Just double check the units at the end. And that's also why some lecturers are very nitpicky about the units, right? Some lecturers are like, if you don't put units and take out marks, right? Because they don't want you to make this mistake, right? They want you to develop habits of keeping track of units, right? So keep track of units, right? Imagine if we say, like, let me show you again why this is important. Imagine if we're saying total distance, right? Total distance in a very simple format. Total distance is equal to 1 kilometer plus 3 miles. And then we say, okay, that's 4 kilometers. That's not true because 3 miles is a bit more, right? So both of them need to be in the same units for us to calculate total distance. You can't just add 1 and 3 and say 4 kilometers because this is in miles, right? 1 kilometer plus 3 miles is not 4 kilometers, right? So it's the same concept here. You need the units to match. Okay, moving on. So 11 should make sense. And number 12 should make sense. Just multiply, right? Double check units, make sure it's standard, right? And then we get to go. Now moving on to number 14. A flywheel has a mass of 60 kg and a radius of gyration of 360 millimeters. Calculate the torque needed to increase the rate of revolution from 4 revs per second to 5 revs per second in 30 seconds. Okay, calculate the torque needed. Okay. So first, let's look at torque. Torque is equal to inertia, right? Times moment of inertia times acceleration, right? How do you find acceleration? Well, we've been given two, an initial and a final and the time. So we already know a formula for that. So this, we're pretty confident we can find that. Revs, we're confident and we can additionally just change it into rads and find that as well. Okay, good. Now I
even deeper than the power of the equation standard for sure.
I, a new formula, I is equal to mk squared, right? Mass, radius of gyration squared. So first we could find I is equal to 60 times 0.36 squared. Again, just plugging the values in. Radius of gyration K is equal to 360 millimeters. Converting that to standard units so that you get this thing that you're familiar with, right? kg meter squared. Like here, 6.0 kg meter squared. Up here, 400 kg meter squared. Okay, so kg meter squared. Multiplying that out, this is already in 60 kg. We divide this by 1,000, changing it to 0.36. Square it, multiply by 60, we get I is equal to 7.776 kg meter squared. Right? Now, acceleration, again, omega 1 is equal to omega 0 plus alpha t. You can do the conversion, or if you already know the conversion, just write this down. Right? That's just omega 1 minus omega 0 divided by t is equal to acceleration. This here is the average angular acceleration formula, which you guys are familiar with. Plug our values in, and notice I just plug 5 and 4 in. So 5 here is final to increase, right? 5 here, 4 here, but both of them are revs, right? Revs per second. So I need to realize that my answer is going to be in revs per second squared. Okay? So 5 minus 4 is 1 upon 30 revs per second squared. Now, in order to convert that into rads per second, right? It's going back up, torque 2, right? You remember this here is 0.4 rads per second squared, and this here is 0.2 rads per second squared. So units in order to get that Newton meter needs to be in rads per second. So I multiply this by 2 pi, which is 2 pi upon 30 rads per second. Now, alternatively, you can break this down into some decimal if you like, right? But I like to keep it like this whole because this makes more sense to me. Using those two things, right? We found I is 7.776 kg meter squared. Put that in. We found angular acceleration as 2 pi upon 30 rads per second squared. Multiply that out. That should give you 1.6286 Newton meters, right? Remember again, you don't need to put it like this. You can put that as some decimal value and you should still get the same answer, right? Okay, so T, we found T to be equal to 1.6286 Newton meters. Right, any questions on this? This is the last question. So if you have any questions, you can go ahead. Okay, no questions.
So to find torque, you need it in rads.
Yeah. Yeah, right? Because remember, these units, right? These units, you need it in rads, find torque. Because you remember that for this here, for this rads here, remember that old formula S is equal to R theta. We can't put revs here. We can't put revs here, right? We need to put rads because that's the whole purpose of using radians, right? And you can always look back at these questions and say, okay, it was rads here, right? It was rads here. Change this to blue. It's rads here. So I need rads to get a Newton meter, right? So that all the units work out. I can't put revs there. I'm not gonna get Newton meters. What I'm gonna get is something like a kg meters squared revs per second squared, something like that, which is some weird thing because the meter and the rads don't get that linear conversion that we would expect from this formula here. Okay, you're not gonna get Newton meters. Okay.
Yes,
And
that's the only concern that we have to know when we have to convert from rads to revs and vice versa.
Yeah. So good rule of thumb for torque, make sure your units in kg meters squared, right? And for the acceleration, make sure it's in rads per second squared. I know I usually don't tell you guys to generalize stuff, think it through, but this for sure, if you want the answers in Newton meters, you can generalize this, right? Make sure I is in these units and make sure acceleration are in rads per second squared. I generalize that, right? For torque. This is the one thing you can generalize. Generalize like that. Just make that generalization, right? And the other thing you should always remember is if you're using formulas like this, right? If you put revs here, you put revs here, put rads here, you put rads here, right? But you can always convert to rads. And if they ask the number of revolutions made, then you can divide by 2 pi, right? You can divide by 2 pi. If we had like 50 rads, if we divide that by 2 pi, we're gonna get 50 upon 2 pi revs, right? Because again, it comes from circle as 2 pi. So 1 revolution is 2 pi rads, right? So we just divide by 2 pi to get number of revs, right? So you can always convert to rads. And then at the end, if they ask for revs, divide by 2 pi. Either way, okay? And just remember these units, right? When you convert for torque, always convert to rads. Or you can just put here in here right? In here, you put 5 by 2 pi, which is 10 pi, which is 10 pi. And this here is 8 pi, right? 2 by 4, 8 pi. And you're going to end up with same 2 pi upon 30, right? You can put rads in here as well. The math works out. So practice them and make sure you understand the concept, right?
Excuse me, sir. Which question will the tests on Thursday coming based on?
I have no idea. No idea. Just be prepared for anything. Obviously, it's not gonna be this, right? Not this, because that's just so short. Everybody can get 100. Not gonna be something like this, because again, that'll take you a minute, right? That is not gonna be this, because this is gonna take you a minute, right? So you're left with 14, maybe 10.
10 or 14. All right, sir.
14,
Sir, can you
10
please?
or 9.
Okay. Okay.
Yeah.
Okay.
So
sir.
it's just common sense, right? Just look at the ones that too easy and just, those ones aren't coming.
Well, sir, excuse me, sir.
Mhm.
Well, when will you be uploading this video, sir? Because I need it. Because seriously, I'm not
I'll upload it. I'll write after class. All right.
Okay, sir. To YouTube, right, sir? All right, sir. Thank you.
One other question, sir. The test is coming on this and the other Newton's laws as well.
I'm not too sure. It's a question for Mr. Sill, right? It's a question for Mr. Sill.
All right.
Yeah. But you guys have the Newton laws handout, right? And the video, I think, is already uploaded. So go ahead and watch
All
that
right, good,
back.
thanks.
Yeah, so just ask Mr. Sill, right? Or maybe she mentioned it in class, but you guys forget. All right, so for the people asking for the solutions in the chat, I emailed this already to you guys, right? I sent the email out yesterday, which should have this.
Yes,
Right,
sir.
so just check your email. All right, good. So that's all I have for you, right? If no other questions, let me just stop sharing and stop.